All right, everybody. We are going to be talking about lipids today. Lipids and fats. Okay, and those two terms, I think at the end of this lecture, you'll have a good sense of and comfort with when is appropriate to use those terms and, kind of like which describes which. Is a fat a lipid and is a lipid a fat? So we will go ahead and get started though. Lipids are substances of biological origin that are soluble in organic solvents. Now, that term organic solvents, one organic solvent that you might be familiar with would be like gasoline is an organic solvent. So lipids, if you ever had uh, yeah, lipids will dissolve in organic solvents. They're not going to dissolve and they're not going to go into solution very well in water by comparison. Now, these are three things that you do need to know. Lipids perform three biological functions. One, they form a bilayer and are essential components of biological membranes. Two, lipids containing hydrocarbon side chains serve as energy stores. That's a really big thing that I want you to be familiar with. They serve as energy stores. Three, many intra and intercellular signaling events involve lipid molecules. So the ways that cells communicate with one another is with the help of lipids. Now, there are five major classifications of lipids. They are fatty acids. So that's where you've probably heard the term, or anytime someone's talking about a fat, they're probably talking about fatty acids, or they're talking about triacylglycerols. If you've ever had a annual physical examination, they did blood work, they probably included a lipid panel. So they checked to see your free fatty acids and your triacylglycerols, as well as, your cholesterol. Um, Glycerophospholipids are a third. Sphingolipids and steroids are the fourth and fifth classes of lipids. We're going to spend a little bit more time on some of these than the others. Now, fatty acids, shown here. On the right-hand side, we've got a total of four different fatty acids. Now, the acid part of this is in reference to this functional group right here. If you notice that functional group, that's a carboxyl group. And anytime you have kind of a chain attached to a carboxyl group, that is an example of a carboxylic acid. So that's where that's coming from. Now, these all look very similar to one another because you've got that carboxylic acid or that carboxyl group, and then at the bottom you've got 18, meaning that there are 18 carbons in this, this, and this. So all four of these different fatty acids, they all have 18 carbons. Now, these are carboxylic acids with long hydrocarbon chains as side groups. The predominant fatty acid residues in plants and animals are between 16 and 18 carbons long. That's an important piece of information that's worth knowing. So we've got our roles of lipids, and then, well, what is the common length of a fatty acid residue? 16 and 18 carbons. Okay. Now, fatty acids fall into two different categories. They are considered either saturated or unsaturated. What gives? What's the difference? Well, we have a notation for that. And actually, before I get ahead of myself, I'm going to go back. Saturated fatty acids in the long hydrocarbon chain, what I want you to notice in that long hydrocarbon chain is there is not a single double bond. Okay, that is your example of a saturated fatty acid. So saturated, I'm going to say no DB, no double bonds. Okay, by comparison, all of these other three fatty acids, those are examples of unsaturated fatty acids. Now, the difference between them is that here we've got two double bonds, one, two, three double bonds. Now, these two right here, I don't know if you're familiar with this prefix, but poly. When you hear that prefix poly, one place that it's commonly mentioned would be like polymer. That's definitely a scientific term. A polyglot is someone who speaks multiple languages. Um, Now, with that in mind, these two fatty acids, these with two and three double bonds respectively, these are considered polyunsaturated fatty acids. And if you've ever talked to a dietitian or someone who, can give adequate and like responsible nutrition advice, they maybe mentioned that consuming a diet rich, I apologize for yawning, rich in polyunsaturated fatty acids is a good idea because, well, polyunsaturated fatty acids are a little bit healthier for most people than your saturated fatty acids. And really, that boils down to how much energy are you consuming, or how much energy do you need? Like if you run 3 marathons a day, don't worry too much about polyunsaturated versus saturated fatty acids. You're running about 78 miles every day. That's a lot. You need as many calories as you can get in a day. That's kind of an extreme. Okay. But here, I want to bring this notation back. C18 colon 0. This is the notation that we use for a saturated fatty acid. C18, that indicates the number of carbons. Then we've got a colon and then a 2. The colon followed by the 2 indicates that there are 2 double bonds in that fatty acid. So if we look at this fatty acid at the end here, it's 18 carbons, and there are 1, 2, and 3 double bonds. We would denote that with C18 colon 3, because we've got 3 double bonds there. Now, all of these double bonds are considered to be in the cis configuration. The first double bond is typically between carbons 9 and 10. And that's just, if you went into a cell and you looked at every single fatty acid, you would typically find that double bond between carbons number 9 and 10. Our polyunsaturated fatty acids follow a pattern. This terminology here, they are not conjugated. What that means is that we've got a double bond followed by a single, followed by a single, followed by a double. I don't want you to stress about that or worry about that. What I do want you to know, however, is I want you to know the difference between saturated and unsaturated fatty acids. I also want you to know the difference between this notation, 18 colon 0 versus 18 colon 2 versus 18 colon 1. A good example question would be something like, which is a polyunsat? I'm going to leave it at that, but polyunsaturated fatty acid, C18 colon 0, 18 colon 1, 18 colon 2, and then all are. And your correct answer for that would be, which one is polyunsaturated? That one right there. That one has 18 carbons and 2 double bonds. Okay, now we can move on. Omega fatty acids. This is something you've maybe heard of. Maybe you've had some advice from somebody that says, oh, well, you should eat lots of omega fatty acids or omega-3 fatty acids. Oh, you should eat salmon or you should eat eggs because they're rich in omega-3 fatty acids. They combat inflammation. Okay, well, where's that coming from? What is this omega? Well, omega is kind of a numbering scheme that's used that is a little bit different, or the omega numbering scheme follows a pattern that what you do is you start from carbon number 18 and count back. So here, these are also known as N fatty acids. And so you'll see them written as C16 colon 1 N minus 3. And that tells you, well, you start from carbon number 16 and you count 3 in. So if we looked at this right here and we said this is an omega-3 fatty acid, and imagine that this is the 16th carbon, we'd say, okay, where's our double bond? First, second, third. Okay, there's our double bond right there. Now, fatty acids, one thing that's important to know about them is saturated fatty acids. As I kind of alluded to earlier, they can be very calorically dense. And the reason for that is they pack super tightly together. Here we've got a picture of a fatty acid that is saturated on the left and one that's unsaturated. The saturated fatty acid is going to pack up really well with other saturated fatty acids, whereas unsaturated fatty acids, well, they kind of have this bend or this kink, which is going to kind of like make them take up more space. Here we've got a picture of, well, here's 5 saturated fatty acids. Look at the space that they occupy. They pack in really well together, whereas unsaturated fatty acids, oh man, here's the same amount of space that was required to get 5 fatty acids, a mixture of saturated and unsaturated fatty acids to pack up. It's considerably larger. Now, what I want you to know with respect to fatty acids, okay, so I want you to know these details. Saturated pack really well, which is why you can get a lot of calories and a lot of energy from a small amount of saturated fatty acids, whereas unsaturated fatty acids don't pack nearly as well. Next up is I want you to know a little bit about the physical properties of saturated fatty acids. Over here, we've got the melting point. The melting point of a fatty acid, look over here on the far left-hand side versus over here, our melting point. We have 12 carbons, 24 carbons. Okay. A 12 carbon fatty acid has a melting point of 44.2 degrees, whereas one that's 24 carbons long has a melting point of 84 degrees. What this means is that as the number of carbons in the chain length increases, so I'll say number of carbons goes up, then the melting point goes up as well. More carbons means longer chains, means higher melting point. Now, at the bottom here, we've got unsaturated fatty acids. This is the fatty acid chain with some double bonds. What I want to do is I want to highlight a couple. So I'm going to scribble this out. I want to compare these 3 right here. Actually, I'll use those 3, and then I'm going to go on to, yeah, there. Okay, so these 3, 18:1 n minus 9, 18:2 n minus 6, 18:3 n minus 3. What are those melting points at? Well, this one is at 13.2 degrees. The next one is -9. So what that means is that at a room temperature is about 23 degrees Celsius, that thing, linoleic acid, is absolutely going to be a liquid. Then our last one, alpha linoleic acid, with a melting point of -17, that too is going to be a liquid at room temperature. And, well, yeah. So as what this tells us is what has changed between these fatty acids is not the number of carbons, but the number of double bonds. So as the number of double bonds increases, what happens to the melting point? The melting point goes down. So there's an inverse relationship between double bond number and melting point. Then if we look down at the bottom, nirvanic acid. Nirvanic acid is a fatty acid with 24 carbons and 1 double bond. Okay, how does the melting point of that relate to oleic acid? Well, oleic acid, 18 carbons, 1 double bond. Nirvanic acid, 24 carbons. So our number of carbons is greater, but the number of double bonds is identical. Our melting point difference is 13.2 versus 39. Okay, so our number of double bonds has remained constant, but our number of carbons has gone up. So what happened to our melting point? That went up too. What I want you to remember is as the number of double bonds increases, the melting point decreases. As the number of carbons increases, the melting point increases. Those 2 factors are very important for you to know. Now, the next slide here just revisits those same saturated fatty acids that we looked at and those unsaturated fatty acids that we saw a little bit ago. But what this tells us is we've got a different numbering scheme and a different kind of naming scheme. We already looked at the omega system where it was n minus something. Here we also have the delta system, delta 9. This numbering scheme tells us where our double bond is. Delta 9, delta 12. Oh, great. We've got a double bond that starts at carbon number 9 and another one that starts at number 12. Last but not least, we've got one that starts at 9, 12, and 15. Delta 9, delta 12, delta 15. So these are kind of the basis and the basics of fatty acids. I think that if you can use the omega numbering scheme, understand the relationship between double bonds and numbers of carbons, and let's just take another quick look through things, how those saturated versus unsaturated fatty acids pack. And then, yeah, I think if you feel good about that, you're going to be in a good place with respect to fatty acids. Now, fatty acids, what they are is they are these kind of free-floating molecules. Those free-floating molecules, however, can react with a molecule known as glycerol. And when they react with glycerol, they form something known as a triacylglycerol. When you get three of these fatty acids to react with glycerol, you form that triacylglycerol. And you get something that looks a lot like this, where it's a glycerol backbone, and then basically the chain of a fatty acid, the chain of another fatty acid, and the chain of a third fatty acid. So a triacylglycerol basically contains 3 times as much energy as a single fatty acid because it's got 3 fatty acids packed in there. Now, fatty acids or triacylglycerols are what are known as fatty acid triesters of glycerol. What I want you to know is that a fatty acid reacts with a glycerol to form a triacylglycerol. Most of these contain 2 or 3 different types of fatty acid residues. The role of triacylglycerols to me is very important for you to know. Triacylglycerols function as energy reservoirs. So, triacylglycerols are basically like a repository that your body has to get a bunch of energy. Now, the fat content of a normal person allows them to survive approximately 2 to 3 months without any sort of calorie intake. So most people walking around could just say, well, I'm not going to eat for 2 or 3 months. And what's going to happen is my body is just going to process the fat that I have stored. Now, I always like to bring this up. There was a guy in England back in the 1960s. Um, I remember his last name was Barbieri, and he fasted for a full year. And this was under supervision of a physician. He fasted for an entire year, and I think he lost somewhere in the order of 310 pounds or so. Um, and what was kind of interesting is that, anytime somebody talks about a diet or making a change, then there's always a kind of critical or cynical person who's like, well, you can't keep the weight off. Well, seemingly this guy did keep this weight off. He didn't eat for an entire year. I just That's something that I always just go like, man, how on earth do you not eat for a year? He took a vitamin and like an electrolyte solution and drank water. Um, but that just it just blows my mind. I've heard of people fasting for like 3 days or 5 days or a month for religious reasons or something, but man, that just makes me go, wow, you did not eat for a year. That's some discipline to say the least. Okay, triacylglycerols function to insulate. Now, back in the 1990s, there was this substance called olestra, which is a carbohydrate-based fat substitute. So basically, what scientists at Frito-Lay did was they said, let's take fat and combine it with sugar, fat plus sugar. And we make something, and that something is called olestra. And this was like a really successful, um, it was a really good and really successful product that was on the market for a little while. There were these things called wow chips. And so it was like foods made with Olestra um, were branded and sold, and people were like, "Oh, this is great! I'm eating Doritos, but they're fat free. Oh my gosh!" But then sometimes when you eat something maybe that's not really real, your stomach says like, "No, I'm not. I ain't about that." And so this was ultimately taken off the market because people just they were having some pretty intense GI issues after the fact. Now, triacylglycerols, one of the things that they are used for is they can be broken down by enzymes in your body known as lipases. Lipases are the enzymes in your body that break down a triacylglycerol to make individual fatty acids, which can then be broken down into, give energy, kind of as an alternative to sugar, an alternative to carbohydrate. Okay, so there's this enzymatic hydrolysis where a triacylglycerol is broken down into individual fatty acids. Well, as an alternative to that, I always like to bring this up. If you've ever been to Cincinnati, Ohio, one of the things that is is very true of people in Cincinnati is that lots of them work for this company called Procter and Gamble. And Procter and Gamble became a big company back in the like 18 I want to say like 1870s or something like that. And what they did was they made soap from pig fat. So they made soap and they did this. They would do this process known as saponification. So this is an industrial process. And this is a critical part of soap making where you take fatty acids or triacylglycerols, um, fat that can be extracted from uh, an animal or something like that, and they'll break it down into basically a soap. And that's going to be helpful for washing your hands or washing your clothes. Okay, so this is our second major lipid that we've talked about. So I'm going to go all the way back to the first slide. Second slide. Fatty acids, triacylglycerols. We've talked about those. Now, we are going to skip over glycerophospholipids and sphingolipids and instead go straight on to steroids. Why? Because they're kind of fun and interesting, and people have a decent understanding or familiarity with steroids. Now, the steroid we're going to talk about is one that you might not necessarily refer to as a steroid, but it is one. Cholesterol. Cholesterol is based on a core structure consisting of three six-membered rings and one five-membered ring. Knowing what cholesterol looks like and being able to identify it is going to be worth your time. So here is a picture of cholesterol. We said one, two, three six-membered rings and one five-membered ring. So this four-ring structure is put together, and that is the most common steroid in animals, and it's a precursor for all other steroids in animals. For example, sex hormones. Steroid hormones bind to highly specific receptor proteins in the nucleus uh, uh, and regulate gene expression and metabolism. Major groups are the sex hormones and those produced by the adrenal cortex. Some of these steroid hormones you've maybe heard of: testosterone, aldosterone, prednisone, prednisolone, cortisol, that's stress hormone, estradiol. So these are all things that you've maybe gotten a little bit of familiarity with. Okay, so when it comes to steroids, I want you to know about cholesterol is a steroid. And then all these other steroid hormones are built based on cholesterol, or they are derived from cholesterol. Now, there are other instances where lipids are relevant to an organism. For example, There's lots of different reactions that take place in your body with the help of different vitamins. Sometimes vitamins are referred to as cofactors. Well, there's four vitamins that are considered lipid-soluble vitamins. And they're considered lipid-soluble because they go into or they don't mix well in water. We've got vitamin A, D, E, and K. The one that we're going to focus on is this guy right here, vitamin D. Vitamin D is a vitamin that you're probably pretty well familiar with. Being in Central Texas, you go outside and you're going to get some successful production of vitamin D because, well, vitamin D needs sunlight in order to be produced. Now, vitamin D is a group of structurally related compounds that play a role in the regulation of calcium and phosphorus metabolism. The most abundant form of vitamin D in the circulatory system is vitamin D3. Now, here what we have. The most abundant form in the circulatory system is vitamin D3, which is this one right here. Okay, so here's what happens. And here's what I want you to know. This compound right here, 7-dehydrocholesterol, that is circulating within your body. When you walk outside, you get exposure to UV light. And UV light is a little bit hazardous because UV light can cause skin cancer as well as other types of cancer. But, well, it can also cause a chemical reaction to take place, and arguably a favorable chemical reaction. Vitamin, or sorry, this 7-dehydrocholesterol is going to be modified in the presence of UV light to make this molecule right here, this vitamin D3. This is known as cholecalciferol. So UV light produces vitamin D3. Now, that is going to be circulating, that's taking place within your skin cells. That's going to be then emptied into your circulatory system, where it can then go to your liver. And then once it goes to your liver, it can go to the kidney and react in these two steps to produce this whole thing right here. This whole thing right here is known as 125 dihydrocholecalciferol. I always want to say that name way too fast. So this is also known as dihydroxyvitamin D3. This compound right here is produced after UV light exposure and then work done by your liver and your kidney. That's one of the things that I want you to know. The production of vitamin D production. Well, I want you to know the sequence. UV light, liver, kidney, and then I'll just say, go! Because once the action has been carried out by your kidney and subsequently, or sorry, your liver and then your kidney, then this vitamin D3 can go all about your body and do what it needs to do. One of the things that vitamin D has been implicated in is there's this rickets. It's this bone disorder where when kids didn't receive adequate vitamin D, their bones would kind of like bow out and they wouldn't be straight. In addition to that, vitamin D is something that lots of people attribute to seasonal affected depression. So if you live in like the Pacific Northwest, Seattle is a great example. Seattle's the place that lots of people always like to pick on for seasonal affected depression. If you live up there, you have really short days, in which case the amount of vitamin D that you get exposure to is going to be less than, say, if you live in like Arizona or something like that, or Central Texas for that matter. And so lots of people will take vitamin D supplements so that they can boost up this 125 dihydroxy vitamin D3. Um, Vitamin D also has some connection to your immune health, but this is kind of our necessary and understood process by which vitamin D is produced. All right. Well, that's what I got. I hope this was helpful. And I hope you have a good one. Thank you very much, everyone. Bye.